Welcome to the Deep Dive. Today we're looking at something pretty fascinating in AI, how large language models, LLMs, are tackling complex games. But maybe not how you'd expect. We're not just talking about them playing games based on intuition. No, we're digging into research where LLMs learn the actual rules and then write the code for the game itself,
Yeah,
becoming a kind of game engineer.
that's right. That's really the mission for us today. We're going to unpack this idea called the Code World Model, or CWM. See, for a while, the standard way was, well, simple. You just ask the LLM, okay, what's the next best move, given the game history? But the research we're looking at makes it clear this has some pretty significant drawbacks. It leans heavily on what they call the model's implicit fragile pattern matching capabilities.
Implicit fragile pattern matching. Okay, that sounds like a core problem. What does that fragility actually mean when the LLM tries to play a game?
Well, it shows up in two main ways. First, the LLM often makes illegal moves that just aren't allowed by the rules. And second, maybe more importantly, its play is often strategically shallow. It's not thinking deeply. It's basically operating in that System 1 mode Daniel Kahneman talked about. Fast, intuitive, pattern-based. Okay.
So it sees something that looks like a good move from games it's seen before,
Oh.
but it doesn't actually check if it fits the rules or the deeper strategy of this specific game.
Exactly. It's like, having a gut feeling but never doing the math. Great for some things, terrible for mastering complex rule systems.
Like trying to build an engine based on vibes. It doesn't work.
Precisely. So the alternative proposed here is a really fundamental shift. Instead of the LLM being the player, it acts as an induction engine. Its job is to generate a formal, executable world model, basically Python code that represents the game, and that's the CWM.
Okay, so if the old way failed because it ignored the rulebook, this new way makes the LLM write the rulebook. That's quite a pivot. What does this CWM code actually contain?
It's essentially a complete simulation engine for the game, but written by the LLM. So instead of just, abstract knowledge, you get concrete Python functions. These functions define things like, first, the state transition, how the game state changes when you make a move. Second, legal move enumeration, what moves are actually allowed right now. Third, termination checks, how do we know when the game is over? And finally, observation and reward functions, what does the agent see and what signals tell it if it's doing well or badly?
So the LLM sets up the entire game logic in code, and then something else uses that code to actually play. What's the process when the CWM agent faces a totally new game?
Yeah, the workflow is pretty clever because it separates the tasks. First, when the agent encounters a new game, it just plays a few random games, really basic stuff just to get some data, some game trajectories. Second, the LLM takes the game rules, written in plain English, and those few trajectories it collected, and uses them to synthesize or write the CWM Python code. Then third, the agent starts playing properly. But instead of asking the LLM for moves, it uses a powerful classical planning algorithm, specifically Monte Carlo tree search, MCTS. MCTS is known for deep look-ahead planning. It runs thousands of simulations to find good moves, and crucially, it runs these simulations using the CWM code the LLM just generated.
Right, okay. The big immediate win seems obvious.
Right.
If the LLM wrote the rules into code and MCTS uses that code, illegal moves should just
Yeah.
disappear, right? It directly tackles that first weakness.
That's exactly the first major advantage they highlight. Verifiability. The Python code is a formal specification. MCTS can literally just call the getLegalMoves function in the CWM. So yeah, assuming the generated code is correct, illegal moves become effectively impossible.
Okay, that makes sense. But the second advantage you mentioned was strategic depth. How does having the LLM write code rather than play make the agent a better player strategically? It feels a bit indirect.
It creates this really powerful synergy, you see. You're combining two different strengths. The LLM brings its massive semantic understanding, its ability to read natural language rules, however complex or messy, and translate them into logical code. That's a huge feat. But then you combine that with the sheer deep search power of MCTS. The LLM does the high-level interpretation and definition work. MCTS provides the brute force calculation for deep tactical planning. It shifts the whole process from that intuitive System 1 reaction to a much more calculated System 2 deliberation using the LLM's output as the foundation.
Got it. The LLM defines the world, MCTS explores it ruthlessly, and the third advantage you touched on was generalization. This seems really important. How does the CWM approach help with games the LLM hasn't specifically trained on, these out-of-distribution or O games?
Well, think about the task. The LLM isn't primarily learning how to play Game X, it's learning the meta task of translating rules and examples into working code. This skill seems to transfer better to new games. It's less about memorizing pattern for one game and more about understanding the process of rule formalization. That's likely why the CWM approach showed it could adapt pretty well to novel games it hadn't encountered during its initial setup. It avoids some of those training data contamination issues you worry about with direct policy models.
Okay, verifiability, strategic depth, generalization, those are compelling. But, I mean, writing code is hard. That first version of the CWM code the LLM spits out, it can't be perfect every time, surely,
Mhm.
especially for a complicated game. Verifiability is great, but only if the verified code is actually correct. How do they handle bugs in the LLM's code?
Right, that's a crucial point. They have an iterative refinement process. So the initial CWM code gets put through its paces using unit tests. These tests are generated automatically from those random game trajectories they collected at the start. If a test fails, like if the CWM code predicts a different game state than what actually happened in the recorded trajectory, it doesn't just fail silently. The error message, including the full stack trace, gets fed back to the LLM.
Ah, like a bug report.
Exactly. The LLM acts like a programmer getting a bug report. It's told, your code broke here for this reason, and then it tries to generate a fixed version of the code. They repeat this process, aiming to get the code's predictions to perfectly match the real game data, basically, reaching 1.0 transition accuracy.
That's really smart. It forces the LLM to learn the rules not just conceptually, but in a way that actually runs and matches reality. Okay, but what about the really messy games? Imperfect information games, IIGs, like poker or bridge, where you don't know the opponent's hand. MCTS typically needs the full picture, right?
Yeah, that's a major hurdle for standard MCTS. Knowing the full state is kind of its thing. So this required adding another layer of LLM synthesis. They tasked the LLM with generating more code, specifically inference functions. These functions try to handle the hidden or latent parts of the state. One approach they called hidden history inference. Here, the generated function tries to guess or sample a plausible full history, including things like what cards were dealt or what hidden moves occurred that would logically lead to the partial history the agent actually observed.
So it's trying to reverse engineer the hidden bits based on the visible clues. Did that work well?
It seemed to perform reasonably well, yeah. A bit better than some other methods in the experiments.
But I remember reading they tackled something even harder called closed-deck synthesis. What was that about? It sounds like a situation where you never get to see the hidden information even after the hand is over.
That's exactly it. It's strict partial observability. Think about playing online poker, where you fold, you might never know what cards your opponent had. To handle this, they did something quite novel. They combined the CWM, the game rules code, and the inference function, the guessing code, into a structure they described as a regularized autoencoder.
An autoencoder. How does that work here?
Well, think of it like this. The inference function acts as the encoder. It takes the partial information the agent sees and makes a guess about the hidden state. Then, the CWM acts as the decoder. It takes that guessed hidden state, runs a simulation using the game rules, and sees if the outcome of that simulation matches the actual observations. The whole thing is then refined based on two things: how accurate the inference guess seems to be in predicting visible outcomes, and crucially, whether the combined code runs without error.
Wow, okay. So the LLM is building this elaborate machine for guessing the hidden world and checking if its guesses make sense according to its own understanding of the rules. That's intricate. Before we jump to the actual results of CWM versus other models, there was one other piece of code the LLM generated, right? Something to help MCTS run faster.
Ah, yes, good point. It also generated code for heuristic value functions, often written as V. These functions provide a quick estimate of how good a particular game state is, usually at the leaf nodes of the MCTS search tree, where the deep search stops. Having a decent estimate there is much better than just simulating randomly to the end, so it speeds up MCTS and can improve the quality of the planning significantly.
Were these heuristic functions refined iteratively like the main CWM code?
No, interestingly, they weren't. The LLM generated a bunch of candidate value functions, and then they essentially held a tournament between them to see which one performed best in practice. That winner was then used. And it's worth noting, this synthesis only turned out to be clearly beneficial for a couple of the simpler games, like generalized tic-tac-toe and a bargaining game. For the more complex ones, the core CWM and the deep MCTS search were the main drivers.
Right, so the core rule writing seems much more critical than the heuristic generation. Okay, let's get to the main event then. The CWM agent, using MCTS on its self-generated code, Went up against a pretty strong competitor, right? Gemini 2.5 Pro.
That's right. They used Gemini 2.5 Pro as the benchmark, specifically using a technique called dynamic thinking, which represents a state-of-the-art approach for using an LLM directly as a policy the old way we discussed. This comparison was done across 10 different games, a mix of perfect and imperfect information, including some novel ode games.
And the big headline, how did the CWM stack up?
The results were pretty stark, actually. The CWM agent either matched or significantly outperformed Gemini 2.5 Pro in 9 out of the 10 games they tested.
9 out of 10, that's a pretty strong statement for the CWM approach.
It really is. It underscores the power of having that verifiable, executable model. For instance, in perfect information games like Connect 4 or that Ode generalized tic-tac-toe, the CWM agent wasn't just winning more, it was achieving near-perfect play. And maybe even more telling when they compared the CWM agent, using the LM-generated code, against a theoretical best, an MCTS agent given the perfect handwritten game code, the ground truth, the CWM agent performed almost identically well.
So the LLM managed to write code that was nearly as good as human expert code for those games. That's impressive.
It shows the potential for LLMs to really nail down complex rule systems into functional logic.
But there was that one game out of 10 where it didn't win. The failure case. Which one was it and what happened?
Ah, yes. The Achilles heel was Gin Rummy.
Gin Rummy. Interesting.
Yeah, the CWM really struggled there. The accuracy of its synthesized code and predicting game transitions was way down, sometimes below 80% in training. And its ability to infer the hidden state in tests was barely better than chance, around 54%. It just couldn't model a game properly.
Why Gin Rummy specifically? It has hidden information, like poker, but poker seemed manageable with the inference functions. What made Gin Rummy so tough?
The researchers diagnosed it as the game's high degree of logical and procedural complexity. It wasn't just the hidden cards, it was the really intricate multi-step scoring phase at the end of a hand. You know, things like deciding when to knock, how players lay off mells on each other's cards, calculating the deadwood points precisely, checking for undercuts. It's this sequence of detailed bureaucratic steps.
It sounds less like a strategic challenge and more like following a complicated administrative procedure.
That seems to be exactly it. These complex, nested procedural subroutines were incredibly hard for the LLM to capture perfectly in code just from seeing a few game examples and reading the rules. Poker rules, while involving hidden state, are perhaps more straightforward procedurally.
That's a really fascinating distinction. The bottleneck wasn't strategy per se, but rule-following complexity. Speaking of strategy, just to double-check, even with this amazing CWM code, deep planning like MCPS is still necessary, right? You can't just teach the LLM to play well directly using the code.
Absolutely. They tested that directly. They tried training a separate policy network using an algorithm called PPO, teaching it to play the game using the CWM as a perfect simulator for training. They called this PPO CWM. And consistently, the original CWM MCTS agent, the one doing the deep search at playtime, outperformed this PPO agent. It was also generally faster to get the MCTS agent working well.
So even if the LLM can write the perfect rulebook, you still need that powerful search engine to actually play well in real time. The intuitive reactive policy still falls short.
Yeah, it strongly suggests that for these kinds of complex strategic domains, online deep search planning offers advantages that are hard to capture just by training a reactive policy, even with a perfect model.
Okay, so let's zoom out. We've gone through the code world model, how it works, its advantages, its limitations. If you had to summarize the big takeaway from this research, what would it be? How should we think about LLMs and strategy now?
I think the fundamental takeaway is that an LLM's greatest strength in these kinds of complex, rule-bound, strategic tasks might not be as the intuitive player making the moves. Its real power could lie in being the high-level architect, the programmer, the one who translates human-understandable rules and intentions into a formal, verifiable, executable system, the world model engineer, essentially.
So what does this all mean for us, for how we might use these models? It feels like we're shifting the burden. Instead of asking the LLM to have brilliant strategic intuition and follow rules perfectly, seems hard, we ask it to focus on the understanding and translation part, creating the verifiable model. Then, we let established methods like MCTS, which are basically just about structured computation, leverage that model to deliver high performance. We turn raw compute power into better play, using the LLM's output as the blueprint.
Precisely. And it leads to a really interesting final thought for you, our listener, to ponder. Think about Gin Rummy again. The CWM struggled most with those fiddly, multi-step procedural subroutines, the bureaucratic parts, but it handled novel O games relatively well. Does this hint that the next frontier for LLM reasoning isn't just about better pattern matching or even high-level strategy, but about mastering the art of generating robust, verifiable step-by-step procedural code? Could it be that the main bottleneck for AI in complex rule-based systems is shifting away from finding clever strategies and more towards just achieving perfect, verifiable, almost bureaucratic adherence to complex instructions? Something to think about until our next deep dive.